Hi, I'm Prof L and welcome to Chemistry Matters, and today we are going to be talking a little bit more about electrochemistry. And again, sort of following on from the previous video, we are going to be looking at quantifying electrochemical cells and I guess figuring out how that all works, figuring out whether something is going to be oxidized, something is going to be reduced. In other words, figuring out what the spontaneous reaction will be whenever we bring together two species that are what we call redox active, that want to either lose electrons or gain electrons. In the last video, we talked about how we could possibly get E-naught values for half reactions. In other words, for a reduction or an oxidation in isolation, okay? We said that we couldn't do that, but what we could do was to sort of fudge things a little bit and measure everything relative to what we call the hydrogen electrode. And the example that we looked at, excuse me, was this one here, where we were taking the hydrogen electrode as being the left-hand electrode and a Cu2 plus to Cu electrode as being the right-hand electrode. And we found that E-naught for that was equal to plus 0.34 volts. We said, okay, E-naught is equal to E of the right-hand electrode minus E of the left-hand electrode, and that was equal to 0.34 volts. E of the left-hand electrode we are arbitrarily assigning as being 0 volts, so that gives E of this process by itself relative to hydrogen as being plus 0.34 volts. Okay, so what that then allows us to do, as I said last time, was to measure the E-naught for any half cell, for any half reaction relative to the hydrogen electrode. And importantly, relative to the hydrogen electrode being the left-hand electrode in any electrochemical cell. Okay. So we do that. We've defined that that's what we can do, so we do it, and when we do that, we end up with this here. Now, it might be a touch difficult to read, but what we have here are the E-naught values for a whole bunch of half cells, or half reactions, half equations, call them what you will, okay? And these are listed in order from the most positive E-naught value in volts, which belongs to fluorine gas at plus 2.87 volts, all the way down to the most negative, which is good old lithium at minus 3.05 volts. Now, we started talking about electrochemistry in terms of the fact that John Goodenough won the Nobel Prize for the development of the lithium-ion battery. And there's a reason why we use lithium in lithium-ion batteries. And that reason is right there, minus 3.05 volts. It turns out that lithium is an extremely good reducing agent, okay? It's very, very happy to get oxidized. Now, excuse me again, let's have a look at some of these values and see what they are showing us. Okay, top of the list, fluorine, that wins. F2 plus 2E minus, giving 2F minus, plus 2.87 volts. Remember, relative to H2, H plus, F2 and F minus, okay? Notice these guys don't have to be balanced as well, just in case you were wondering. We dispense with that. We're simply showing what is the reduced version and what's the oxidized version, okay? So in other words, when we set up this electrochemical cell, it's got an E-naught of plus 2.87 volts. And because it's positive, that means that reduction is occurring at the right-hand electrode. It means that oxidation is occurring at the left-hand electrode. And reduction is occurring really, really, really strongly at the right-hand electrode because of the fact that the E-naught is massive for this, plus 2.87 volts. So fluorine is the world's best oxidizing agent. In this particular cell here, the overall equation, okay, the overall equation for what's going on here is going to be F2 plus 2E minus going to 2F minus, okay? And that is going to be a reduction, and the oxidation is going to be H2 or a half H2 plus an electron, whoops, of course not, going to H plus E minus, okay? And again, if we're going to make sure that the number of electrons transferred are the same, which we always should, then we would multiply this guy by 2, and we would get the overall equation F2 plus H2 giving 2F minus plus 2H plus, okay? And hopefully that is overall a balanced equation. So this will be a spontaneous reaction. Fluorine will oxidize hydrogen. It will end up as fluoride. The hydrogen will end up as H plus. Okay, so in other words, F2 is a very strong oxidizing agent. Now, as we go down and down and down, you can see that the E-naughts become smaller and smaller and smaller. Surprise, surprise, surprise. Until we get to H2, okay? Or 2H plus 2 electrons giving H2. And that has got an E-naught of 0 volts because that's the way that we defined it. And the interesting thing then happens when we go to negative E-naught values. So let's see what that means. And so let's say, what do we choose? We'll go cobalt, why not? Cobalt 2 plus. So we will go cobalt 2 plus and cobalt. Let's set up that electrochemical cell. And we know that in that electrochemical cell, E-naught of the cell is equal to E-naught of the right hand minus E-naught of the left hand. And what we're going to find is the E-naught of that cell is minus 0.28 volts. A negative value. Now, we have always assumed, and we always will assume, because that's the way that you do that, that reduction is occurring here at the right-hand electrode and oxidation is occurring at the left-hand electrode, okay? Now, as long as your E-naught is positive, that is true. That reduction is occurring at the right-hand electrode and that oxidation is occurring at the left-hand electrode. But what happens when we get an overall negative value? Aha, negative value means that, well, first we're getting ahead of ourselves there. We'll save the big reveal for a second or two. Let's write out the defined cell reaction, the cell reaction that corresponds to this particular cell diagram. So we're always assuming that reduction's occurring at the right-hand electrode. So we would go CO2 plus 2 electrons giving CO, and we would go H2 giving 2H plus 2 electrons. So the overall, the defined cell reaction would be CO2 plus H2 giving CO plus 2H plus. Good, okay, but E-naught for that, E-naught of the cell is minus 0.28 volts. Now remember, E-naught for a cell is E-naught of the right-hand electrode minus the E-naught of the left-hand electrode. Left-hand electrode 0, we know that. Right-hand electrode is negative. So therefore the overall E cell is going to be negative as well. So that means that this defined cell reaction is not spontaneous. Okay, it's not spontaneous. Now if you think back to good old thermodynamics, we had this thing called delta G, and delta G, remember, just to confuse you, if delta G is negative, the process is spontaneous. If delta G is positive, the process is not spontaneous. Now, some genius thought, let's switch the signs in electrochemistry, and so now, if you've got an electrochemical cell whose E is positive, then that process is spontaneous. If it's negative, the process is not spontaneous. It's the reverse process that is spontaneous. Okay? So in this case, this defined cell reaction here is not spontaneous. The spontaneous process is going to be CO plus 2H plus giving CO2 plus H2. In other words, cobalt is going to reduce H plus to H2 and get oxidized in the process. Okay, so that is what a negative value of an E-naught means. Okay, if E-naught is positive, it means that the oxidizing agent in your half cell is going to oxidize H2 to H plus. And if E-naught is negative, it means that the reducing agent in your half cell is going to reduce H plus to H2. And I said that quite quickly. I'm trying not to confuse you here, folks, but that's really, really, really important stuff. Okay, and we're going to continue on with that by looking at now an example. Okay, so let's say we've got Ag plus Ag, and we've got Cu2 plus Cu. We've got those two half cells. So the question then becomes, and this is the sort of question that you'll get in final exams, what is going to be the spontaneous process if we essentially bring those two half cells together? Okay? So in other words, if we have, let's say, a solid silver electrode and that's dipped in some Ag+, so silver nitrate solution, something like that, and you've got a solid copper electrode dipped in some copper sulfate, let's say, and you can connect the electrodes, put in a salt bridge, what's going to happen? Okay, what's the spontaneous process going to be? So the one thing that we do need to know in order to get the answer here is the E-naught values for those half cells, okay? So the E-naught for this half cell is equal to plus 0.8 volts, and we've already seen the E-naught value for this cell is plus 0.34 volts. Okay, so given those pieces of data, what is going to be the spontaneous process that occurs? Okay, right, so let's figure out what the possible processes that could occur are. Okay, and it's helpful that we write it sort of like this because that helps us to show that there's really only two possible reactions that you can get. And so let's write that Cu2 plus and Cu there. Right, so what are the two processes that can occur? What are the two possible reactions that can occur? Well, we can have a reaction between Ag plus and Cu, and we'll put little arrows there, or you could have a reaction between Cu2 plus and Ag. And that's it. Those are the only two possible processes that you could have in this, as a result, I guess, of bringing these two half cells together. Okay? So in other words, Ag plus will react with Cu to oxidize Cu to Cu2 plus and be reduced to Ag. That's one possibility. Or the other one is that Cu2 plus can oxidize Ag, Cu2 plus gets reduced to Cu, Ag gets oxidized to Ag plus. Right, so which one is it going to be? Well, once we're given these values here, once we're given the E-naughts of the cell, then it becomes hopefully fairly obvious. So E-naughts are for that particular half cell. In this case, whoops, let's take out the cell there. E-naught is equal to plus 0.8 volts, and in this case, E-naught is equal to plus 0.34 volts. Okay, so what we're going to do is we're going to set up two imaginary electrochemical cells. Okay, one in which this is going to be the right-hand electrode, and the other in which this is going to be the right-hand electrode. Let's set them both up and see what answer we get when we do that. Okay, so first up, let's have the silver one as the left-hand electrode. So silver plus going to silver and copper 2 plus going to copper. Okay, and let's write that, as an oxidation, because that's the assumption. Remember, oxidation occurs at the left hand, reduction occurs at the right hand. So therefore, E-naught of this cell is going to be E of the right hand minus E of the left hand. E of the right hand is 0.34 volts, minus E of the left hand is plus 0.8 volts, minus 0.8 volts, and remember that's positive, and so therefore that comes out as being minus 0.46 volts. Aha! We have our answer. We have our answer because the E-naught of this cell is negative when we have copper at the right-hand electrode. In other words, when we have Cu2 plus being reduced and silver being oxidized. That's not going to happen. That is not spontaneous. Okay, so the defined cell reaction for this is going to be Cu2 plus being reduced to copper, and it's going to oxidize Ag plus 2Ag plus. That's the defined cell reaction. The defined cell reaction says we have reduction occurring at the right-hand electrode. Copper 2 plus to copper, silver being oxidized to Ag plus. Okay, and that, everybody, is not spontaneous. Okay, so that gets the big cross. That's not happening. Okay, so what about then the other way around? The other way around has to be spontaneous. If this is not spontaneous, the other way has got to be spontaneous. So let's write that out now. We've got now silver at the right hand, we've got copper at the left hand. So your defined cell reaction for this now is going to be silver plus getting reduced to silver and copper being oxidized to copper 2 plus. Okay, E-naught of this cell is equal to E of the right hand minus E of the left hand, which is equal to silver is plus 0.8 volts, the left hand minus plus 0.34 volts, and that is equal to plus 0.46 volts, and that is positive, and that means that this reaction is going to be spontaneous. Okay? So what we have done there is that we have shown the same thing in two different ways. Okay? We've drawn our two possible cell diagrams, and we've figured out what the defined cell reaction is from those two possible cell diagrams. In both cases, assuming that reduction takes place at the right-hand electrode. We showed for the first one that E-naught is negative, not spontaneous. We showed for the second one, when you swap them around, E-naught is positive, spontaneous. Done. Okay? And that is the way that you can find out what the spontaneous process is going to be given the E-naught values for any half or any two half cell reactions, okay? For any two half cells. Now, I am aware that they do this differently in different parts of the world, okay? But IUPAC, who are the gods in all of this, I guess, what they say goes, never, ever, 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 ever change the sign on a reduction potential, okay? Remember that list of potentials? They were all written as reductions. You keep the same sign even if it's not a reduction that you're talking about. Here, for example, this is an oxidation, but the E-naught for this is still plus 0.34 volts. You don't change the sign on it, okay? So never, ever, ever change the sign on a reduction potential, and you can't go wrong. Always assume that the E of the cell is the E of the right hand minus E of the left hand, and you're done. Now, again, I realize that some students find this confusing. You've just got to follow the conventions in all of this. And if you follow the conventions, you can't really go wrong. Hopefully, anyway, okay? Right, so I think that's all I've got to say to you on this. This is good, solid stuff. As I said, it's good, solid exam fodder. Sort of long answer type questions, you know, find out the spontaneous process that will occur if you bring these two together, etc., 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 that sort of stuff. So hopefully with what you've learned today, you can now go away and ace those particular types of questions. Okay? Right, so having said all that, we will see you in the next video.